The Arrhenius equation is a mathematical formula that describes the temperature dependence of chemical reactions. It is named after the Swedish chemist Svante Arrhenius, who first proposed it in 1889. The equation relates the rate constant K of a chemical reaction to the temperature T and the activation energy A of the reaction. K equals a times exp R, T where is the pre-exponential factor sometimes called the frequency factor, R is the gas constant, and exp is the exponential function. The Arrhenius equation shows that the rate constant of a reaction increases exponentially with increasing temperature. It also implies that the activation energy is related to the temperature dependence of the reaction rate, and that a higher activation energy leads to a more temperature-sensitive reaction. The Arrhenius equation is widely used in many branches of science and engineering, including chemistry, physics, materials science, and chemical engineering. Applications of Arrhenius equation. The Arrhenius equation is a mathematical equation that relates the rate constant of a chemical reaction to temperature. It is commonly used in the field of chemical kinetics and has several applications in various scientific and engineering fields. Here are some notable applications of the Arrhenius equation. Chemical kinetics. The Arrhenius equation is primarily used to study the temperature dependence of reaction rates. By measuring reaction rates at different temperatures, the Arrhenius equation can be used to determine the activation energy A of a reaction and the frequency factor in the rate equation. This information helps in understanding the reaction mechanism and predicting reaction rates at different temperatures. Thermal analysis. The Arrhenius equation is widely used in thermal analysis techniques such as differential scanning calorimetry (DSC) and thermogravimetric analysis (TGA). These techniques involve measuring changes in sample properties, such as heat flow or weight loss as a function of temperature. The Arrhenius equation can be applied to analyze the thermal behavior of materials, including decomposition reactions, oxidation, phase transitions, and degradation kinetics. Materials science. The Arrhenius equation finds applications in materials science and engineering for studying the temperature-dependent properties of materials. It helps determine parameters such as diffusion coefficients, activation energies for diffusion, and thermal stability of materials. These insights are crucial for designing materials with specific properties and understanding their behavior under different thermal conditions. This information is also useful to synthesize various compounds. Pharmaceutical industry. In pharmaceutical research and development, the Arrhenius equation is utilized to evaluate the stability of drugs and predict their shelf life. By conducting accelerated stability studies at elevated temperatures, the reaction rate constants can be determined using the Arrhenius equation. This information allows for estimating the degradation rate of drugs at typical storage temperatures and establishing appropriate storage conditions. Environmental science. The Arrhenius equation has applications in environmental science, particularly in modeling and predicting chemical reactions in atmospheric chemistry. By considering the temperature dependence of reaction rates, the Arrhenius equation helps in understanding the kinetics of important processes such as pollutant degradation, atmospheric reactions, and photochemical reactions. Thermal treatment processes. Industrial processes involving heat treatments, such as metal heat treatment or polymer curing, can benefit from the Arrhenius equation. By understanding the temperature dependence of reaction rates, process parameters can be optimized to achieve desired material properties or efficient processing conditions.